Turbomachinery. This chapter introduces the fundamental concept of turbomachinery as machines that transfer energy between a fluid and a rotating shaft. These machines are central to many engineering systems, such as pumps, turbines, compressors, and fans. The main focus is how mechanical energy and fluid energy are converted through the interaction between flow and blades. Understanding this concept is essential to analyze performance, efficiency, and operating limits of fluid machines. This chapter serves as a foundation for more detailed pump and turbine analysis.
Lesson Plan, Fluid Mechanics 2. This slide shows the position of turbomachinery within the overall structure of the Fluid Mechanics 2 course. Previously, the course covered viscous flow, external flow, compressible flow, and open channel flow. Turbomachinery represents a direct application of those flow concepts in real systems. With this sequence, students are expected to already have a strong foundation to understand rotating fluid machines. This topic closes the course with highly practical and industry-relevant applications.
Learning outcome. The learning outcomes describe the competencies that should be achieved after completing this chapter. Students are expected to identify various types of pumps and turbines and understand their working principles. In addition, students should be able to use dimensional analysis for designing geometrically similar machines. Vector analysis of inlet and outlet velocities is also an important focus. Finally, the concept of specific speed is used as a basis for preliminary pump and turbine selection.
Turbomachinery in real applications. This image shows a real example of turbomachinery in the form of an aircraft jet engine. The engine combines a compressor and a turbine in a highly complex system. Air is compressed, burned, and then expanded through the turbine to generate thrust. This shows that turbomachinery is not only used in power plants, but also in modern transportation systems. This example emphasizes the importance of this topic in modern engineering.
Pump and turbine operation. This slide explains the fundamental difference between pumps and turbines from an energy perspective. A pump adds energy to the fluid so that the outlet energy is higher than the inlet energy. In contrast, a turbine extracts energy from the fluid and converts it into mechanical work. This difference in the direction of energy transfer is what fundamentally distinguishes their functions. This concept becomes the basis for all subsequent performance analysis. Steady flow in pumps. The discussion starts with the assumption of steady flow inside the pump. Under this condition, the mass flow rate entering the pump equals the mass flow rate leaving it. For incompressible fluids and equal cross-sectional areas, the inlet and outlet velocities can be considered the same. The main role of the pump is to increase the fluid pressure between the inlet and the outlet. This concept links mass conservation with the practical function of a pump. In steady flow, the mass flow rate entering the pump equals the mass flow rate exiting, ensuring continuity.
Gas handling devices. This slide classifies gas handling devices into fans, blowers, and compressors based on pressure rise and flow rate. Fans produce a small pressure rise but a large flow rate and are commonly used for ventilation. Blowers operate in the middle range with moderate pressure and flow rate. Compressors produce a large pressure rise, but with a relatively smaller flow rate. This classification is important for selecting the right device for a given system.
Manual pump mechanisms. Examples of manual pumps are shown through a tire pump and a hand well pump. Both devices work using an up and down motion to move or compress the fluid. The energy used comes entirely from human power, not from a motor. These pumps do not use a rotating shaft and therefore belong to non-rotating pumps. This example shows that pump principles do not always require rotating systems. Biological and mechanical analogies. The images of the human heart and a water meter show an analogy of positive displacement pumps and turbines. The heart works as a pump that moves a certain volume of blood in each heartbeat cycle. The water meter works on a similar principle, but is used to measure flow volume. Both operate based on displacing a fixed volume per cycle or revolution. This analogy helps to understand the positive displacement concept in a more intuitive way.
Positive displacement pump and turbine examples. This slide explains in more detail how the heart and the water meter work as positive displacement devices. Valves in the heart ensure one-directional flow during the pumping of blood. The water meter uses small chambers that fill and empty to measure fluid volume. The basic principle is the controlled and measurable displacement of volume in each cycle. The main difference lies in the purpose, namely biological circulation versus flow measurement.
Correct answer, B. Both function as positive displacement devices, moving or measuring fluid by displacing a known volume per cycle. Explanation of incorrect options. Option A. The heart operates using biological energy, not electrical energy, and water meters typically use fluid motion to drive their mechanisms rather than external electricity. Option C. While the heart circulates blood continuously for life support, a water meter does not circulate fluids but measures the volume of water passing through. Option D. The heart does not use a turbine mechanism, and only specific types of water meters might involve turbine-like components. Positive displacement is the key concept here. Wind turbine dynamics. This slide introduces the wind turbine as an example of a dynamic, open fluid machine. Air flows through the blades and causes the rotor to rotate due to kinetic energy transfer. The kinetic energy of the wind is converted into mechanical energy on the turbine shaft. This mechanical energy is then used to drive an electric generator. This example shows how turbomachinery can directly utilize natural energy sources. Pump head and power. The pump head is defined as the energy difference between the pump inlet and outlet. This head is usually represented as a change in the energy grade line relative to a reference plane. The input power to the pump is expressed as brake horsepower, supplied by the motor or driver. The pump converts this mechanical energy into fluid energy in the form of increased pressure and elevation. This concept becomes the basis for calculating power requirements and pump performance. Centrifugal pump performance. This slide shows the performance curves of a centrifugal pump that relate head, efficiency, power, and flow rate. Every pump has a most efficient operating point, called the best efficiency point, or BEP. At this point, the pump operates with maximum efficiency and relatively minimal vibration and losses. If the shaft rotational speed is changed, the shape of the performance curves will also change. Therefore, selecting the proper operating condition is very important for system efficiency. Pump operating point. The pump operating point is defined as the intersection between the pump curve and the system curve. The system curve shows the required head as a function of flow rate, based on the piping system resistance. At this intersection point, the pump capability and the system requirement are in balance. Ideally, the operating point should be close to the BEP to achieve high efficiency. This concept is very important in practical pump design and selection.
The operating point of a pump is the flow rate where the performance curve intersects the system curve, balancing supply and demand. Multiple operating points in pumps. In some systems, the pump curve and the system curve may intersect at more than one point. This condition can cause operational instability because the pump may shift between operating points. As a result,
The flow rate and pressure may fluctuate undesirably. This problem usually arises from a mismatch between pump and system characteristics. The solution is to change the pump or modify the system so that only one stable operating point exists. Pump role in piping systems. Pumps play the role of increasing pressure so that the fluid can flow through the piping system. They are also used to lift fluids to higher elevations against gravity. In real systems, there are always energy losses due to friction and piping components. The pump must supply additional energy to compensate for these losses. Therefore, the pump becomes a key component to ensure the flow system can operate properly. Fan performance data insights. Fan performance data show how the head varies with the flow rate. Initially, the head increases as the flow rate increases, but after a certain point, the head decreases. This behavior indicates the performance limit of the fan. The head data for fans are usually expressed in terms of water column height, even though the working fluid is air. This is a standard practice in the ventilation industry. Centrifugal pump performance plot. This plot shows a complete set of centrifugal pump characteristics for different impeller sizes. Changing the impeller diameter modifies the relationship between head and flow rate. It also shows efficiency zones that help identify the optimal operating region. The NPSH required curve is included to ensure cavitation-free operation. Such a chart is very important in real-world pump selection. Pump selection considerations. Pump selection is not determined only by the maximum efficiency listed in the catalog. In many cases, a slightly less efficient pump may consume less energy if its operating point better matches the system requirement. The main key is to align the pump best efficiency point with the system operating point. Commercial limitations often mean that a perfectly ideal pump is not available on the market. Therefore, pump selection is always a compromise between theory and real conditions. Correct answer: B. Because the less efficient pump's operating point better matches the system's requirements, reducing unnecessary energy use. Explanation of incorrect options. Option A. The size or capacity of the pump does not inherently determine energy usage. It depends on how well the pump matches the system's operating conditions. Option C. Less efficient pumps are not designed to minimize energy use. Their reduced energy consumption in this scenario comes from better alignment with system demands. Option D. A more efficient pump does not always operate at a higher flow rate. Efficiency relates to energy transfer, not necessarily the flow rate. Cavitation in impellers. Cavitation occurs when the local pressure on the suction side of the impeller blade drops below the vapor pressure of the fluid. Under this condition, vapor bubbles form and are carried to regions of higher pressure. These bubbles collapse suddenly and cause noise and vibration. The collapse process can also gradually damage the impeller blade surface. As a result, cavitation reduces efficiency and shortens pump life. Pump performance and NPSH. The pump performance curve shows that the head decreases as the flow rate increases. At the same time, the required NPSH increases with increasing flow rate. For safe operation, the available NPSH from the system must always be greater than the required NPSH. If this condition is not satisfied, cavitation will occur. Therefore, NPSH analysis is an important part of pump system design. Cavitation and maximum flow rate. A pump can operate without cavitation as long as the available NPSH is greater than the required NPSH. At a certain maximum flow rate, these two values become equal and the safe operating limit is reached. If the flow rate is increased beyond this point, cavitation becomes unavoidable. This condition causes performance degradation and risk of mechanical damage.
Therefore, the maximum pump flow rate is often limited by cavitation rather than by the motor. Pump arrangement challenges. Combining different pumps in one system can create various operational problems. In a series configuration, differences in head flow characteristics can cause instability. In a parallel configuration, unequal flow sharing can cause some pumps to operate outside their safe limits. These problems arise due to mismatched pump characteristics. Therefore, careful analysis is required before combining multiple pumps in a system.
Correct answer B. The potential for instability or inefficiency caused by mismatched head flow characteristics or unequal flow sharing. Unequal flow sharing. Explanation of incorrect options. Option A. Electrical overloading is not typically the primary issue when combining pumps. The main concern lies in hydraulic performance mismatches. Option C. Pumps can usually operate simultaneously, but mismatched characteristics can lead to inefficiencies or danger rather than inability to meet flow rates. Option D. Physical alignment may require attention, but is not the critical issue in terms of operational stability or efficiency. The primary concern is hydraulic compatibility.
Combined pump performance in series. This graph shows how pumps arranged in series produce a total head equal to the sum of the individual pump heads. At very high flow rates, some pumps must be shut off and bypassed. If this is not done, the pumps may be forced to operate outside their safe region. This condition can actually reduce the combined head and damage the equipment. Therefore, bypass arrangements are an important part of series pump systems.
Series pump performance insights. In a series system, the total head is always the sum of the individual pump heads at the same flow rate. However, each pump has an operating flow limit that must not be exceeded. If one pump reaches its limit, it must be shut off and bypassed. For identical pumps, this problem usually does not occur because all pumps operate at the same flow rate. This principle is very important in high-pressure system design. Turbomachinery. This part marks the transition to a more systematic discussion of pump configurations, especially series and parallel arrangements. The main focus is how head and flow characteristics change when multiple pumps are combined. This approach is essential in industrial systems that require flexibility in capacity and pressure. Understanding these concepts helps avoid operating pumps outside their safe limits. The analysis is still based on pump and system characteristic curves.
Parallel pump performance. Insights. In a parallel configuration, the total system capacity is the sum of the individual pump flow rates at the same head. If one pump exceeds its shut-off head, it must be turned off to prevent damage. Valves on each branch are required to prevent reverse flow through inactive pumps. If the pumps are identical, load sharing becomes stable and selective shutdown is unnecessary. Proper selection and configuration determine system efficiency and reliability. Positive displacement pump types. Peristaltic pumps work by squeezing a flexible tube using rollers, so the fluid never contacts the pump mechanism. Rotary lobe pumps transfer fluid using two interlocking lobes with smooth flow and low shear. Gear and screw pumps use intermeshing rotating elements to produce nearly constant flow. These types are well suited for viscous fluids or high-precision applications. The basic principle is to move a fixed volume every cycle.
A peristaltic pump delivers precise flow without fluid contamination by using rotating rollers to compress a flexible tube.
Parallel pump configuration. Parallel configurations are used when the system requires very large flow rates. The main advantage is flexibility because pumps can be turned on or off according to demand. The system also becomes more reliable due to redundancy if one pump fails. This arrangement allows energy savings under partial load conditions. However, the characteristics of each pump must still be compatible to ensure stable flow sharing.
Two-lobe rotary pump operation. The fluid is transferred using a positive displacement principle by being trapped between the lobes and the casing. Two rotors rotate in opposite directions, pushing packets of fluid toward the outlet. The process consists of intake, trapping, transfer, and discharge phases. Each lobe moves a separate volume of fluid without mixing. This design produces relatively smooth flow and is suitable for sensitive fluids.
Pump performance and viscosity. An increase in fluid viscosity causes a reduction in net head and narrows the free delivery range. This means the pump works harder and the motor is more prone to overload. Therefore, the pump must be operated within the range recommended by the manufacturer. The shaded region on the curve indicates conditions that should be avoided. Pump selection must consider the working fluid viscosity. Correct answer, B. It reduces the net head and narrows the free delivery range, potentially leading to inefficiencies. Explanation of incorrect options. Option A. Increased viscosity decreases the net head and limits the free delivery range instead of increasing or extending these parameters. Option C. Increased viscosity significantly impacts the operating range, making this option incorrect. It requires adjustments to avoid inefficiencies and motor strain. Option D. Increased viscosity generally reduces pump efficiency as more energy is required to move the fluid, contrary to what this option states.
Self-priming pump. A self-priming pump can operate even when the casing is initially empty of fluid. The system usually includes a hose or special mechanism to draw fluid from the source. This type is very useful for applications that require suction lift. Examples include draining flooded areas or transferring water from a lower level. Its main advantage is easy startup without manual priming. Dynamic pump impeller categories. Centrifugal flow impellers accept fluid axially and discharge it radially to produce high head. Mixed flow impellers combine axial and radial characteristics for moderate requirements. Axial flow impellers move fluid parallel to the shaft and are suitable for large flow rates with low head. Each type is selected based on system head and capacity requirements. This classification is important in the early stages of pump design and selection. Centrifugal blower uses a spiral-shaped casing to direct airflow efficiently. Mechanical energy from the motor is converted into kinetic energy and pressure in the airflow. This equipment is widely used in HVAC systems and industrial processes. Its design allows large volumes of air with good directional control. The working principle is very similar to a centrifugal pump for liquid fluids. Centrifugal pump overview. The fluid enters axially through the eye at the center of the impeller. The rotating impeller throws the fluid radially outward, increasing its kinetic energy. The diffuser, or scroll-shaped casing, slows the flow and converts velocity energy into pressure. The impeller geometry strongly determines the flow rate and energy transfer efficiency. Overall, the shaft mechanical energy is converted into fluid energy in the form of head. Check your understanding. Number 8. This question emphasizes the fluid entry path and the main role of the impeller in a centrifugal pump. The fluid enters through the eye at the center of the impeller and is then accelerated radially by the rotating impeller. This process converts shaft mechanical energy into the fluid's kinetic energy. Understanding this is important to visualize how pressure is eventually built in the casing. This concept becomes the basis for velocity and velocity triangle analysis in the following slides. Centrifugal pump blade types. Backward inclined blades provide high efficiency and stable power characteristics. Radial blades are used for medium pressure applications with moderate efficiency. Forward inclined blades can deliver high flow rates, but require higher power input.
The choice of blade type strongly affects the performance curves and power consumption of the pump. Therefore, blade design is a key decision in pump engineering. Velocity analysis in centrifugal pumps. The analysis is performed by examining the normal velocity components at the impeller inlet and outlet. The impeller functions to convert mechanical energy into fluid motion. The casing and scroll then guide the flow toward the outlet with minimal energy loss. This approach allows a quantitative evaluation of pump performance. All discussions are still based on the control volume concept. Velocity vectors in centrifugal pumps. Fluid motion is described using absolute and relative velocity vectors. The relative velocity follows the blade surface in the rotating frame of reference. The relationship between these two vectors forms the velocity triangle at the inlet and outlet. From this triangle, flow angles and tangential components can be determined. This information is essential for calculating pump head and power.
Angular momentum in centrifugal pumps. The torque applied to the shaft causes a change in the fluid's angular momentum. The tangential velocity components at the inlet and outlet determine the magnitude of this change. Using a control volume approach, the relationship between torque and flow rate can be analyzed. This principle forms the basis of Euler's turbomachinery equation. Energy transfer inside the pump is essentially governed by this change in angular momentum. Law of cosines in pump analysis. The law of cosines is used to relate velocity magnitudes and angles in the velocity triangle. With this approach, each velocity component can be calculated systematically. These calculations allow more accurate determination of head and power. The accuracy of flow angle measurement becomes very important in design. Small errors in angles can have a large impact on performance prediction. Correct answer B. To analyze velocity components and angles for precise calculation of head and power. Explanation of incorrect options. Option A. Velocity triangle analysis focuses on velocity components and flow angles, not the physical dimensions of the pump components. Option C. While material strength is critical in design, velocity triangle analysis does not involve assessing impeller blade durability. Option D. Velocity triangle analysis does not predict temperature changes. It is used to understand the relationship between velocity, angles, and energy transfer in the pump. The analysis is performed in a reference frame relative to the rotating impeller. The Bernoulli equation is modified to include rotational effects and energy transfer. In this ideal approach, irreversible losses are neglected at first. The goal is to understand the main mechanisms of pressure and velocity change. This approach forms the basis before introducing real loss corrections. Velocity vectors at impeller inlet. The absolute velocity shows the actual direction and magnitude of the fluid entering the impeller. The relative velocity shows how the fluid moves relative to the rotating blade. Decomposing these into tangential and normal components helps to understand the fluid-blade interaction. From this, it can be analyzed whether the inlet flow matches the design angle. Mismatch in angles can cause losses and efficiency reduction. The importance of rotation rate conversion. The rotational speed must be expressed in radians per second for consistent calculations. Using RPM directly can lead to errors in dynamic analysis. Unit consistency is critical in all equations involving angular velocity. Many design mistakes originate from neglecting this unit conversion. Therefore, this step must not be ignored in turbomachinery analysis. Impeller blade design variations. All blade designs share the same inlet and outlet angles, but the angular distribution along the radius is different.
This difference is intended to accommodate the change in tangential speed from the hub to the tip. The blade shape strongly affects how the fluid is accelerated and guided. The scaled diagram shows how these geometric variations are visually compared. Optimizing blade shape is the key to achieving high efficiency. In pump design, blade shapes are adjusted to achieve specific flow characteristics for efficiency, while the leading and trailing edge angles remain consistent across all designs. Blade design trade-offs. Too few blades increase circulatory flow losses and reduce efficiency. On the other hand, too many blades cause passage blockage and higher friction losses. A good design must balance these two effects. The main goal is to maximize energy transfer with minimum losses. Therefore, the choice of blade number cannot be arbitrary.
Performance gap analysis. The difference between theoretical and actual performance is mainly caused by irreversible losses. Pump designs are usually optimized at a specific operating condition called the design point. Outside this condition, the actual performance deviates from the prediction. Therefore, test curves are very important to represent real pump behavior. Understanding this gap is essential in real engineering applications.
Axial flow pump aerodynamics. Axial flow pump blades generate lift using a principle similar to an airplane wing. The flow follows the blade contour smoothly to minimize separation. Downward deflection of the flow produces an upward lift force on the blade. This mechanism allows efficient energy transfer to the fluid. This aerodynamic concept forms the basis of axial pump and fan design.
Helicopter rotor dynamics. Rotor blades generate lift due to a pressure difference between the upper and lower surfaces. Lower pressure above and higher pressure below create an upward force. The airflow is pushed downward through the rotor plane, known as downwash. This principle is identical to how axial pumps move fluid. Therefore, helicopter rotors are often used as an analogy in turbomachinery discussions.
Correct answer, B, by producing a pressure difference with low pressure above and high pressure below the blades. Explanation of incorrect options. Option A. Uniform pressure on both sides of the rotor blades would not generate lift. Lift relies on a pressure difference. Option C. Helicopter rotors do not compress air like a piston. They function by directing airflow and creating pressure differences. Option D. Lift is not generated by reversing airflow or creating suction below the blades. It is created by the pressure difference due to the aerodynamic shape of the blades. Axial flow fan configurations. Axial fans can operate as open fans like propellers to produce thrust or free airflow. In other applications, the fan is placed inside a duct to improve directionality and cooling effectiveness. This flexibility makes axial fans widely used. The basic principle remains the same, which is to push fluid parallel to the axis of rotation. The main difference lies in the casing arrangement and flow environment.
Rotor blade twist design. The blade pitch angle is made larger near the root and smaller near the tip. This is done to compensate for the increase in tangential speed with radius. With a twisted design, the angle of attack can be kept nearly constant along the blade. The result is a more uniform lift distribution and higher efficiency. This design is very important in modern propellers and axial fans.
Velocity vector computation. Near the blade root, the relative velocity is influenced by lower tangential speed and higher pitch angle. Near the tip, the higher tangential speed changes the orientation of the velocity vector. Therefore, velocity vectors must be computed at several radii. A graphical approach is often used to understand these changes. The goal is to ensure optimal flow distribution along the blade.
Induced swirl dynamics.
The rotation of the blades causes the surrounding fluid to rotate as well, creating swirl. This swirl is part of the energy transfer process from the rotor to the fluid. If not controlled, swirl can become a source of energy loss. Blade and stator design aim to manage or eliminate unnecessary swirl. With proper control, system efficiency can be improved.
Fan performance insights. Fan head decreases as the flow rate increases, indicating limitations in energy transfer capability. Fan efficiency reaches a maximum value at an optimal flow rate. Beyond this point, efficiency decreases even though the flow continues to increase. Meanwhile, brake horsepower keeps rising as the flow rate increases. This shows that operating at high flow rates requires much more energy.
In fan performance, the head decreases as the flow rate increases, while the efficiency reaches its maximum at an optimal flow rate before declining.
Axial fan configurations. Tube axial fans produce swirl in the exiting flow and are suitable for simple applications. Counter-rotating fans use two impellers rotating in opposite directions to eliminate swirl and improve efficiency. Vane axial fans use a stator to straighten the flow after the rotor. These configuration differences mainly aim to manage swirl and improve energy utilization. The choice of type depends on efficiency requirements and system complexity.
Axial flow fan types and features. Tube axial fans are usually belt-driven and do not have stator blades, so they produce swirl. Vane axial fans use direct drive and stator blades to reduce swirl and improve efficiency. This difference affects energy consumption and the quality of the outlet flow. For high-performance applications, vane axial fans are preferred because the flow is better controlled. Meanwhile, tube axial fans are simpler and easier to maintain.
Vane axial flow fan analysis. The rotor imparts angular momentum to the flow, while the stator corrects the flow direction. In the absolute reference frame, velocity components before and after the rotor and stator can be analyzed. In the relative reference frame, the focus is on the fluid velocity relative to the rotor blades. This dual approach helps to understand energy transfer and swirl formation. This analysis is very important for designing high-efficiency axial fans. Fan performance curves. Performance curves show that head decreases as the flow rate increases. Efficiency reaches a peak at an optimal operating point. Beyond this point, even though the flow increases, efficiency decreases. Brake horsepower keeps increasing with flow rate, indicating higher power demand. These curves form the main basis for fan selection and operation. Correct answer, B. The head decreases as flow rate increases and brake horsepower steadily rises with higher flow rates. Explanation of incorrect options. Option A. The head does not increase with flow rate. It decreases due to energy transfer limitations, and efficiency does not continuously decrease but peaks at an optimal flow rate. Option C. Efficiency does not continuously improve with flow rate. It peaks at an operational sweet spot and declines beyond that range. Option D. Brake horsepower increases with flow rate, as higher flow rates demand more energy input, making this option incorrect. Multi-stage axial flow pump uses multiple rotor-stator pairs to increase fluid energy step by step, so that the total pressure can be raised without overstressing a single stage. Each stage adds kinetic energy and pressure to the flow, making the overall system more efficient for high-pressure applications. The rotating hub maintains smooth and consistent flow from one stage to the next. This concept is widely used when a single stage cannot provide the required head. In practice, the multi-stage approach allows a more compact and reliable design. Multi-stage axial flow turbo machine.
This figure illustrates the staged arrangement of rotors and stators working sequentially along the flow direction. Each blade row adds or redirects the fluid momentum before it enters the next stage. The visualization clarifies that the total pressure rise does not come from a single impeller, but from the accumulation of many stages. The flow remains predominantly axial, making it suitable for large flow rates with gradually increasing head. The figure emphasizes the importance of stage integration within one machine.
Multi-stage axial flow turbomachine. This multi-stage turbomachine shows the staged concept applied to a complex system such as a jet engine. The fan, low-pressure compressor, and high-pressure compressor work in sequence to raise the air pressure before combustion. The high-pressure and low-pressure turbines then extract energy to drive the upstream stages. Each component has a specific role in the energy conversion chain. Overall, the system demonstrates how many small stages can deliver very high performance. Dimensional analysis of pump. Dimensional analysis is used to summarize the relationships between flow rate, pipe diameter, velocity, and fluid properties into dimensionless groups. With this approach, the effects of density, viscosity, and friction can be studied systematically without testing every possible size. This method is essential in pump design and testing because it allows experimental results to be generalized. Operating variables, such as rotational speed, can also be included in a consistent framework. The result is a theoretical basis for similarity laws and scaling.
Flow parameters describe the relationship between flow rate, pipe diameter, and velocity profile, incorporating factors like friction, density, and viscosity.
Scaling geometrically similar pumps. Two pumps are dynamically similar if all their dimensionless parameters are the same. Under this condition, the ratios of flow rate, head, and power follow well-defined scaling relationships. This concept allows engineers to test a small model to predict the performance of a large prototype. As long as geometric and dynamic similarity are satisfied, the test results can be transferred with confidence. This approach saves both cost and development time. Non-dimensional pump performance curves collapse the behavior of similar pumps of different sizes into a single universal curve. In this way, the best efficiency point can be compared without depending on the absolute size of the pump. This approach is very useful for selecting the right pump within the same design family. Design consistency can be maintained even when the physical size changes. In practice, this simplifies performance evaluation and selection. Scale model testing. Small-scale pump models often show lower efficiency than full-scale prototypes. Therefore, empirical corrections are needed to estimate the actual efficiency at large size. Even so, model testing remains very valuable for understanding performance trends and flow characteristics. By applying similarity laws, the model results can be extrapolated to the prototype. This approach is standard practice in turbomachinery engineering. Dimensional misuse in pump analysis. Specific speed is actually a dimensionless parameter, but it is often misused with inconsistent units. This mistake can lead to wrong interpretations in pump selection and comparison. Maintaining dimensional consistency is essential to keep the analysis physically correct. Proper practice ensures that comparisons among designs remain meaningful. This slide emphasizes the importance of discipline in using dimensionless parameters. Correct answer: B. Using dimensional quantities instead of maintaining dimensional consistency for a dimensionless parameter. Explanation of incorrect options. Option A. Specific speed is independent of the type of fluid. It is a parameter derived from flow, head, and rotational speed, not fluid properties. Option C. Specific speed can apply to a range of pump types, not just centrifugal pumps. Limiting its application is not the common misuse. Option D.
While friction and energy losses are critical in pump analysis, specific speed itself is a geometric and flow-related parameter not directly influenced by such losses. Specific speed conversion ratios. In practice, there are differences between the dimensionless specific speed, the US version, and the European version. Conversion ratios are used to relate them numerically under assumptions such as standard gravity. Standardizing to 4 significant digits helps maintain numerical accuracy. Understanding these conversions is important when comparing data from different references. In this way, misinterpretation across unit systems can be avoided. Efficiency versus specific speed. Dynamic pump types, such as centrifugal, mixed flow, and axial flow, can be classified based on their specific speed ranges. In general, the maximum efficiency increases with specific speed up to a certain point, then decreases for very high-speed axial pumps. Centrifugal pumps are suitable for low flow rates and high head, while axial pumps are suitable for high flow rates and low head. Mixed flow pumps lie in between as a transition. This chart helps in selecting the most appropriate pump type for a given system. Affinity laws for pumps. The affinity laws show how flow rate, head, and power change when the shaft speed is varied. The flow rate is directly proportional to rotational speed, so increasing RPM immediately increases capacity. The head is proportional to the square of the speed, meaning the energy requirement rises much faster than the flow. The power is proportional to the cube of the speed, so a small increase in RPM can cause a large increase in power demand. These relationships are crucial for predicting the consequences of changing operating speed. Pump speed effects. When pump speed is increased, the head rises rapidly, but the power rises even faster. This explains why the driving motor often becomes the main limiting factor in increasing operating speed. Without proper monitoring, the pump can be overloaded and operate beyond safe limits. Therefore, speed control must always be linked to motor capacity and mechanical strength of the system. This slide emphasizes the need for caution when increasing pump speed. Pump head increases rapidly with speed, while brake horsepower grows even faster, highlighting higher energy demands and the need for careful monitoring to prevent overloading. Pump performance insights. This plot shows that as the flow rate increases, the net head decreases significantly. The efficiency increases with flow rate until it reaches a maximum value, then decreases again at very high flow rates. There is an optimal operating range where the compromise between head and efficiency is the best. This example shows that a pump should not be operated arbitrarily outside its optimal region. The choice of operating point strongly determines performance and equipment lifetime. Affinity laws application. The affinity laws apply not only to speed changes, but also to changes in impeller diameter. By knowing the desired ratios of head and flow, the new diameter can be estimated systematically. This approach is very useful in design modifications or retrofitting existing systems. Dimensional analysis ensures that geometric changes remain physically consistent. In this way, design adaptation can be done without starting from scratch. Historical windmill insights. Traditional windmills in the 19th century were mainly used for grinding grain and other mechanical tasks. The partially covered blades were necessary so that the wind flow could be used effectively. Although the technology was simple, the principle of converting wind kinetic energy was already well applied. Modern wind turbines are essentially an evolution of the same concept with aerodynamic and material optimization. This slide shows the continuity between old and modern technology. Nutating disc flow meter. This device measures volumetric flow rate using the motion of a disc that nutates inside the casing. Each cycle of motion represents a fixed volume of fluid passing through the meter. By counting the number of cycles, the total flow volume can be determined accurately. This design belongs to the positive displacement category. Therefore, it is widely used in residential water meters.
Correct answer. B. By utilizing the motion of a nutating disc to measure the volume of fluid passing through the meter. Explanation of incorrect options. Option A. Nutating disc meters do not compress fluid or use screws. They rely on the motion of the disc to measure volume. Option C. While turbine meters measure flow velocity using rotational speed, nutating disc meters operate based on volume displacement, not velocity. Option D. Vibrating diaphragms are not part of the nutating disc meter mechanism. They are used in different flow measurement technologies.
Nutating disc flow meter. This figure shows the internal cutaway of the device to illustrate how the fluid drives the disc motion. The flow path and disc movement mechanism are displayed to clarify the working principle. Each disc motion is converted into a mechanical signal or a numerical reading. This visualization helps explain that the measurement is based on discrete volume, not flow velocity. This is why the device remains accurate even at low flow rates.
Examples of dynamic turbines. These examples show that the dynamic turbine principle is not only used in power generation, but also in instruments and aeronautical applications. An anemometer uses a small turbine to measure wind speed based on the kinetic energy of the flow. In research aircraft, turbines can be installed to extract energy from wingtip vortices. Both examples rely on converting fluid kinetic energy into mechanical rotational energy. This confirms the versatility of turbomachinery concepts in many fields.
Pelton-type impulse turbine. The Pelton turbine operates by using a high-velocity water jet that strikes the buckets on the wheel. The kinetic energy of the jet is converted into mechanical rotational energy through a change in momentum. The bucket design with a splitter ridge divides the jet into two streams to maximize flow deflection and impulse force. This turbine is very suitable for applications with very high head and relatively small flow rate. The pure impulse principle distinguishes it from reaction turbines.
Pelton-type impulse turbine. This figure shows the Pelton wheel with a series of buckets designed to receive a high-velocity water jet. Each bucket has a special shape to deflect the flow almost 180 degrees so that the momentum change is maximized. This arrangement ensures that most of the jet kinetic energy is transferred to the wheel. The visualization confirms that there is no significant pressure change inside the runner, only changes in velocity and flow direction. This explains why the Pelton is classified as a pure impulse turbine.
Pelton wheel and generator. This slide shows the Pelton wheel together with a generator to illustrate the energy conversion chain from water to electricity. The potential energy of water is converted into jet kinetic energy, then into mechanical rotational energy, and finally into electrical energy. The detailed bucket design aims to maximize the efficiency of capturing jet energy. This system is very suitable for sites with large elevation differences. This example also shows the integration between fluid machinery and electrical machines. The Pelton wheel converts the kinetic energy of water jets into mechanical rotation, making it ideal for high-head operations where significant potential energy can be harnessed.
Pelton wheel system. This figure provides an overall view of the Pelton system, from the nozzle to the turbine wheel and the driving shaft. The water jet is precisely directed to the buckets to ensure optimal energy transfer.
The generator is directly coupled to the shaft to minimize mechanical losses. This visualization helps to see the system as a whole rather than as separate components. In this way, the energy path from fluid to electricity can be fully understood. Bottom view of operating Pelton wheel. This bottom view shows how the water jet strikes the buckets and is split by the splitter ridge. The direction of wheel rotation is determined by the reaction force from the deflected water flow. The bucket shape ensures that the water leaves with a relatively low velocity, so that energy loss is minimized. This visualization emphasizes the importance of bucket geometry in determining turbine efficiency. The interaction between the flow and the rotating mechanism can be directly observed from this perspective.
Velocity diagram for Pelton bucket flow. This diagram shows the velocity vectors of water as it enters and leaves the bucket. By separating relative and absolute velocities, the momentum change can be analyzed quantitatively. The splitter ridge divides the flow into two symmetric paths to balance the forces on the wheel. This analysis forms the basis for calculating the force and power produced by the turbine. The vector approach clarifies the relationship between bucket geometry and turbine performance.
Theoretical efficiency of Pelton turbine. The theoretical maximum efficiency is achieved when the bucket speed equals half of the jet speed. Under this condition, the momentum change and energy transfer become optimal. The rotational speed of the wheel depends on the jet velocity and the wheel radius. If the bucket speed is too small or too large, part of the jet energy will be wasted. This principle is a key guideline in designing the operating speed of a Pelton turbine.
Correct answer, B. The bucket speed must be half the jet speed, ensuring optimal energy transfer and minimal losses. Explanation of incorrect options. Option A. If the bucket speed equals the jet speed, the relative velocity between the water and the buckets becomes zero, leading to inefficient energy transfer. Option C. The wheel radius is typically fixed during operation. Efficiency is determined by the relationship between jet speed and bucket speed, not by dynamically adjusting the radius. Option D. Water jets striking the buckets at angles greater than 90 degrees would result in improper impact, reducing efficiency instead of maximizing it.
Unlike impulse turbines, reaction turbines operate with a combination of velocity and pressure changes inside the runner. Water flows through the volute and is guided by stay vanes and wicket gates before entering the runner. The wicket gates can be adjusted to control the flow rate and power output. Many reaction turbines use a vertical axis for a more compact design. This concept shows that energy is extracted from the fluid through both pressure and velocity. Subcategories of reaction turbines. This slide classifies reaction turbines into Francis radial flow, Francis mixed flow, propeller mixed flow, Kaplan, and propeller axial flow types. The main differences lie in the flow direction relative to the runner and whether the blades are adjustable or not. Each type is designed for a specific range of head and flow rate. This classification helps engineers select the most suitable turbine for site conditions. By understanding the flow direction, performance characteristics can be better predicted.
Francis radial flow turbine. This Francis radial flow turbine is shown as an example of a large-scale application with a very large runner diameter. With 17 blades, it is designed to produce hundreds of megawatts at medium to high head. The large flow rate indicates its capacity for large hydroelectric power plants. The combination of runner geometry and operating conditions determines the overall efficiency of the system. This example emphasizes how mechanical and hydraulic design must work together. Francis mixed flow turbine highlights. This Francis mixed flow turbine shows how radial and axial flow are combined in one runner design. With a large diameter and relatively low rotational speed, it is suitable for large-scale hydroelectric power plants. The very high power output indicates efficient conversion of water energy into mechanical energy. The large flow rate confirms that this design is intended for rivers or dams with high discharge capacity. This example illustrates the trade-off between head, flow rate, and machine size.
Propeller turbine highlights. This propeller turbine is designed for low head and high flow conditions. With fewer blades and a large runner diameter, water can pass through the runner with minimal resistance. The power output is smaller than that of large Francis turbines, but it is well suited for sites with small elevation differences. This example shows that not all power plants require high head to produce useful power. The choice of turbine type must always match the hydraulic site conditions.
The turbine is equipped with 5 blades of 12.7 feet diameter and operates with a flow rate of 63.7 meters cubed per second, making it suitable for low-head hydroelectric applications. Hydroelectric plant setup. This layout shows the complete energy conversion path from the reservoir to electricity. The head gate controls the flow into the penstock, which then delivers pressurized water to the turbine. The Francis turbine converts hydraulic energy into mechanical energy on the shaft. The draft tube is used to recover part of the kinetic energy before the water is discharged to the tail race. The whole system demonstrates the importance of each component in maintaining plant efficiency. Efficiency in pumps and turbines. Efficiency is defined as the ratio of useful output to input and is always less than unity. For pumps, efficiency compares the water horsepower to the shaft horsepower supplied. For turbines, the definition is reversed, comparing the mechanical output power to the water energy input. This difference reflects the different functions of pumps and turbines. The concept of efficiency is a fundamental basis for evaluating fluid machine performance. Correct answer B. Turbine efficiency measures the ratio of water energy input to mechanical output, the inverse of pump efficiency. Explanation of incorrect options. Option A. Turbine efficiency is not equal to pump efficiency. They are inversely related, with one focusing on water energy input and the other on mechanical energy input. Option C. Turbine efficiency does not compare mechanical output to shaft horsepower input. That description applies to pump efficiency, not turbines. Option D. Turbine efficiency accounts for both water energy input and mechanical output, not just water energy losses. Hoover Dam Overview. The Hoover Dam is shown as a real-world example of turbomachinery applied on a very large scale. Its massive concrete structure is designed to withstand water pressure while directing the flow to the turbines. The hydraulic turbines inside drive generators to produce large amounts of electricity. This project shows how civil and mechanical engineering work together in an energy system. In addition, the dam has become an important symbol of sustainable energy technology. Velocity vectors in Francis turbine. This diagram shows the relationship between relative velocity, absolute velocity, and blade motion at the outer radius of the runner. Velocity triangles are used to describe the direction and magnitude of tangential and normal velocity components. From this, the exchange of energy and momentum between the fluid and the runner can be analyzed. The blade angle beta strongly determines the flow direction and the amount of energy transfer. This approach is the basis of reaction turbine performance analysis. Velocity vectors at inner radius. At the inner radius, the velocity triangles have a different orientation compared to the outer radius. This change reflects how the flow is guided and decelerated as it moves toward the runner's center. Analysis at this location is important to ensure that the flow enters the runner without separation or major losses. The relationship between relative and absolute velocities remains the key in energy calculations. By understanding both locations, the runner design can be optimized as a whole. Reverse swirl phenomenon. Reverse swirl occurs in Francis mixed-flow turbines when operating at very high power and flow rates. Under this condition, the exit flow direction can become opposite to the runner rotation. This phenomenon can reduce efficiency and cause operational instability. The flow pattern in the draft tube becomes abnormal and can induce vibrations. Therefore, such extreme operating conditions should be avoided in practice. Reverse swirl in Francis turbines occurs under high power and flow conditions, causing fluid to exit in a direction opposite to the runner rotation, potentially reducing efficiency and causing instability. CFD analysis of runner blade pressure. CFD analysis is used to study the pressure distribution on the Francis turbine runner blades by modeling one blade passage and replicating it by symmetry. The highest pressure appears at the leading edge on the pressure side, while the lowest pressure is on the suction side near the trailing edge. The color contour map helps visualize static pressure variations along the blade surface. This information is important to identify areas prone to cavitation or wear. With this approach, blade design can be optimized before physical manufacturing. Two-stage steam turbine overview. This two-stage steam turbine consists of high-pressure and low-pressure stages to extract energy step by step from steam. Each stage has blades designed to guide and accelerate the steam flow optimally. The staged arrangement allows more efficient use of steam energy than a single stage. Such systems are common in steam power plants. The staged concept reduces losses and increases overall efficiency. MS 7001F gas turbine rotor. This rotor shows the integration of multi-stage compressors and turbines on a single shaft. The gas flow passes through stators and rotors sequentially to undergo compression, combustion, and expansion. The high rotational speed and large power output indicate large-scale industrial application. This layout emphasizes the importance of balancing aerodynamics and mechanical strength. This example illustrates the complexity of modern turbomachinery. Wind turbine design categories. This slide classifies wind turbine designs based on the rotation axis and the force principle used. Horizontal axis turbines dominate modern applications because of their high efficiency. Vertical axis turbines can be drag-based or lift-based with different operating characteristics. In addition, there are special concepts such as diffusers and concentrators to enhance energy capture. This classification helps explain why so many wind turbine design variations exist. Correct answer, C. They rely on aerodynamic lift for operation, featuring designs such as Phi Darius and Gyromill turbines. Explanation of incorrect options. Option A. This describes drag-type turbines, not lift-type turbines. Lift-type turbines rely on aerodynamic lift rather than drag for rotation. Option B. Savonius and Shield turbines are examples of drag-type turbines, which are not relevant to lift-type turbine operation. Option D. Directional operation, e.g. upwind, is a characteristic of horizontal axis turbines, not specifically of vertical axis lift-type turbines. Wind energy applications. Wind energy applications are expanding worldwide to reduce dependence on fossil fuels. Integrating wind turbines into buildings shows a new approach in sustainable architecture. This example demonstrates that wind turbines are not only placed in open fields, but also in urban environments. This approach broadens the opportunities for renewable energy utilization. Design innovation becomes the key for wide acceptance of this technology. Wind turbine power curve. The wind turbine power curve shows the relationship between wind speed and the generated power. At the cut-in speed, the turbine starts to rotate and produce power. At the rated speed, the power reaches the designed maximum value.
At the cut-out speed, the turbine is shut down to prevent damage due to excessive loads. This curve is essential for evaluating turbine performance under different wind conditions.
Wind turbine disk area. For a horizontal axis turbine, the swept area is circular and determines how much wind energy can be captured. For a vertical axis turbine, the effective area is rectangular. This frontal area is the main parameter in calculating wind power potential. The larger the area, the more energy can be extracted from the flow. This concept explains why rotor size strongly determines generating capacity.
The swept area of a horizontal axis turbine is represented by a circular disk, while a vertical axis turbine exhibits a rectangular disk area based on its blade orientation.
Control volume in wind turbine analysis. The control volume approach is used to analyze the airflow around a wind turbine. A large control volume encloses the entire stream tube to observe global changes in velocity and pressure. A small control volume focuses on the rotor region to compute forces and power. The streamlines expanding downstream indicate energy extraction from the flow. This method provides a physically consistent analysis framework. Streamwise profiles in wind turbines. The velocity profile shows that the flow slows down as it passes through the turbine disk because part of its energy is extracted. The pressure profile rises upstream of the turbine and drops sharply across the rotor. These changes in velocity and pressure are directly related to the aerodynamic power extraction. Streamwise analysis helps visualize the energy extraction process. In this way, the working mechanism of wind turbines can be understood quantitatively.
Key concepts in derivatives. Derivatives are used to find the maximum and minimum values of a function by identifying critical points. A critical point is obtained by setting the first derivative equal to 0. In engineering, this approach is essential for optimizing designs and system performance. Many optimization problems, including those in turbines and pumps, rely on this concept. Therefore, understanding calculus becomes an important tool in engineering analysis.
Correct answer, B. By solving the derivative of a function equal to 0 to identify potential maxima or minima. Explanation of incorrect options. Option A. The second derivative test is used to determine the nature of critical points, maxima, minima, or points of inflection, but not to find the critical points themselves. Option C. Integrals calculate the area under a curve and are unrelated to locating critical points for maxima or minima. Option D. Graphing provides a visual approximation but is not a precise analytical method for determining critical points. Wind turbine performance. Wind turbine performance is often expressed in terms of the power coefficient, which indicates the fraction of wind energy that can be extracted. The theoretical maximum is given by the Betz limit, and no design can exceed it. Horizontal axis turbines generally have better performance than vertical axis turbines. Nevertheless, practical values are always below the theoretical limit due to aerodynamic and mechanical losses. This concept emphasizes that design optimization always faces fundamental physical limits. Dimensional analysis in turbines shows that performance is governed by parameters such as head, flow rate, and rotational speed. A characteristic diameter of the runner or discharge is used as the main length scale. By forming dimensionless groups, general relationships among these variables can be obtained. This approach allows comparison among turbines of different sizes. In addition, this method forms the basis for model testing and scaling to prototypes. Dimensional similarity in turbines. This topic discusses dimensional similarity in turbines, which allows performance comparison between machines of different sizes but similar geometry.
By using dimensionless parameters, the relationships among head, flow rate, diameter, and rotational speed can be analyzed consistently. Geometric similarity ensures that the flow pattern remains relatively the same. Dynamic similarity ensures that the ratios of dominant forces are also the same. This approach is the foundation for scaling from model to prototype. Pump turbine functionality. A pump turbine system operates in two modes, as a pump and as a turbine. During low electricity demand, the system pumps water to an upper reservoir to store potential energy. During peak demand, the stored water is released and the machine operates as a turbine to generate electricity. Using the same machine for both modes increases system flexibility. This concept is the backbone of modern pumped storage power plants. Large pump turbine runner. This image shows a very large pump turbine runner used in a pumped storage power plant. The large physical size reflects the very high flow rate and power capacity. The blade design must withstand significant mechanical and hydrodynamic loads. Besides structural strength, the blade shape is also optimized for flow efficiency. This illustration emphasizes the real industrial scale of turbomachinery applications. Key features of Yards Creek pump turbine. The Yards Creek pump turbine has 7 runner blades designed for efficient energy conversion. Its outer diameter of more than 5 meters allows a very large flow rate. The rotational speed of 240 RPM is selected to match the required head and power conditions. The power output reaches over 100 megawatts, showing its utility-scale application. The high net head ensures effective energy storage and release. Check your understanding. This section contains a practice question intended to test understanding of pump turbine characteristics. The focus is on linking technical specifications, such as blade number and rotational speed, to operational function. Such questions help ensure that the concept is not only memorized, but also functionally understood. In the lecture flow, this part is usually skipped as instructed. The main focus remains on the underlying technical concepts. Conversion ratios for specific speed. This slide discusses conversion ratios between the dimensionless definition of specific speed and the U.S. customary unit definition. The calculation usually assumes Earth's gravity and water as the working fluid. With these assumptions, the conversion factors can be derived consistently. The ratio values are written with high precision using several significant digits. This is important to avoid misinterpretation when comparing design data. Turbine types versus specific speed and efficiency. This diagram shows the relationship between turbine types, specific speed, and the maximum achievable efficiency. Impulse turbines are suitable for low specific speeds with relatively lower efficiency. Francis turbines operate in the mid-range with very high peak efficiency. Kaplan or propeller turbines are used at high specific speeds with similarly high efficiency. This chart serves as a first guideline for selecting turbine type based on head and flow conditions. Turbine efficiency versus specific speed. This slide emphasizes again that turbine efficiency is strongly influenced by specific speed. Each turbine type has its own optimal operating range. When operating outside this range, the efficiency drops significantly. Therefore, matching the operating conditions with the turbine type is very important. This approach ensures an economical and reliable design. Turbine-specific speed. Specific speed is defined as a parameter that characterizes turbine performance for different combinations of head and power. This parameter is formulated in a dimensionless form so it can be used for cross-design comparisons. Mathematically, specific speed combines rotational speed, power, and head into a single expression. This value does not represent physical size, but the hydrodynamic behavior of the machine. Therefore, specific speed is very useful for turbine classification and scaling.
Correct answer. B. To characterize turbine performance under varying head and flow conditions, enabling comparison and scaling of designs. Explanation of incorrect options. Option A. Specific speed is a dimensionless parameter used for performance characterization, not for determining physical dimensions of a turbine. Option C. While rotational speed may be considered in specific speed calculations, its primary purpose is to evaluate and compare performance, not to directly determine rotational speed. Option D. Specific speed does not measure a turbine's lifespan. It focuses on performance metrics for design and comparison.
References. This section lists the main reference used in the discussion of turbomachinery, especially the textbook by Chengel and Chimbala. This reference serves as the theoretical foundation for all concepts about turbines, pump turbines, and specific speed that have been discussed. Using this textbook ensures that the definitions, diagrams, and analytical approaches follow international standards. With a clear reference, students can trace back the derivations and more detailed explanations. It also confirms that the lecture material is based on well-established and credible engineering literature.